Luca, take over.
Okay. Okay, the record is not starting yet, so I can start actually.
You start. Live stream is start now.
Okay, so can I start?
Yeah.
Okay, welcome everybody. So it's my pleasure to introduce Mihir Seth from IC Bangalore, and he will talk about Eichler-Shimura relation and Galois representations attached to modular forms. So Mihir, over to you.
Yeah. So thanks for the introduction, Luca, and I thank organizers for inviting me again to give one more talk in this trimester program. So today I'm talking about the Eichler-Shimura relation and Galois representations attached to modular forms. Yeah, as the title says here. Yeah, so I hope everybody can hear me well and see my screen so well. Okay, so first of all, let's jump to the main theorem of this talk. Okay, so this is due to Eichler and Shimura. So take a normalized eigenform of weight 2 and a cuspidal normalized eigenform of weight 2 for the group gamma 0 n. So this has a Fourier series like this, and so I'm assuming for simplicity that all these Fourier coefficients are rational numbers. In general, they belong to some number field. So given such a form and any prime L, there exists a unique representation of the absolute Galois group of Q on two-dimensional vector space over QL. So let's denote this representation by rho FL. And this representation is unique for the following property, that for all primes not dividing in an L, rho FL is unramified at P. And then the characteristic polynomial of rho FL of Frobenius at P is x square minus APX plus P. So I'm assuming that the audience knows what it means for a Galois representation to be unramified at a given prime. So okay, so quickly. So we have this absolute Galois group of rational numbers, and it contains the absolute Galois group of periodic numbers for every prime P up to conjugation by some element in this group. And by unramified at P, I mean that if you look at the inertia subgroup of that local Galois group, local absolute Galois group, that inertia subgroup acts trivially. So this is the definition of unramified at P. And then when a representation is unramified at P, one can talk about the Frobenius element at P, because the representation factors through the Galois group modulo inertia, which is isomorphic to the absolute Galois group of the finite field FP, and which is generated by this Frobenius element at P. So what does this theorem say? It says that given a nice modular form, one can attach a Galois representation such that the action of the Frobenius, the trace of the action of the Frobenius recovers the Fourier coefficients of the modular form that we begin with. So this is the trace of the Frobenius, and this is the determinant of the Frobenius. Okay. Right. So this talk is about explaining what ideas go into proving this theorem. It's the proof is very technical, and I don't understand all the details myself. I tried to read it. I will explain whatever I have understood. And
what is the reference?
Yeah, I will give the reference at the end. Or
when was the theorem proved?
This was proved, I think, in 70s. I'm not very
I
sure.
think 1959.
Oh, 59.
I don't know. I'm just asking.
No, okay, I don't know, but I was thinking around 70s, I think. I don't know, sir. So, okay, so since Professor Kulkarni asked about references, maybe I will go at the end slide where I have written all the references. So so this reference I talked in my last talk as well, right? The book by Diamond and Schulman, it's called The First Course on Modular Forms.
So
Although it's called
this,
yeah.
they prove this theorem in detail in this book.
Yes. In the
Okay.
last 4 chapters, which are quite advanced, they prove this theorem in detail. But many details are left in exercises.
Oh.
Then if you want to have a look at the original ideas of Eichler and Shimura, which I haven't read the original paper, but then Brian Conrad has written appendix in these lecture notes on Serre conjectures by Ribet-Einstein, and these are also very nicely written, but again very advanced. And
So Conrad had talked about the motivation and background. Huh?
Sorry.
Conrad had talked about the background and motivation of Eichler-Shimura.
Background motivation is there, but not much. Yeah, some background motivation is there.
What
Okay,
is
and the
this
second
Major's
and third.
theorem?
Sorry.
What is this Major's theorem?
Yeah, so the second and third references are for, I'm coming to that part.
Okay.
Yeah, so so the main theorem that I stated is proved in the first reference and also in the fourth reference. Okay. Okay, so the plan of my talk is the following. So it's divided into 3 sections. In the first section, I'm going to talk about elliptic curves over arbitrary fields. For now, we have seen elliptic curves over C, but one can define this over any field, and that requires the language of algebraic geometry, which I'm assuming some familiarity with the algebraic geometry in this term. So for the section 2, in the section 2, I will talk about Jacobians and the action of the Hecke operator TP on certain Jacobian J0. And in the third section, I will explain the Eichler-Shimura relation and the sketch of the proof of the main theorem.
TP is Hecke operator.
TP is Hecke operator. Yeah. Okay, so let's begin with elliptic curves or arbitrary fields. So let K be a field. And for me, curves, by curve over K, I mean a smooth, irreducible, projective variety of dimension 1 defined over K. Okay. So instead of saying this all the time, I will just say curve over K. So let X be a curve over K. And then we saw in Schoenak's talks that one can talk about the divisors on X. So what are divisors on X? So these are just formal sums of points on X. So any element is nx, where nx are integers and they are 0 for all but finitely many of X. Okay, so and then inside these divisors, so this divisors on X form a group, abelian group, and then inside this we have principal divisors, which are the divisors coming from the function field of my curve X. So take any f in Kx, that is the function field of X, and then the corresponding divisor is actually the sum over zeros and poles of X, that function multiplied with the the corresponding order of that 0 and 4. So these are the principal divisors of X. And then for any divisor D, we can define a degree of D to be just the sum of the integers appearing, non-zero integers appearing in that divisor. So it's a theorem, very elementary, that the principal divisors they are degree 0 divisors. So I have the group of divisors on X. Inside this, I have degree 0 divisors on X. and degree 0, they contain the principal divisors of X. So we denote the quotient of degree 0 divisors by principal divisors by peak 0x. So peak 0x is the quotient of degree 0 divisors modulo principal divisors on X. And
I think just a question, given a function field
yes,
of one variable,
yes, they will, yeah.
You are using some theorem about curves, that there is a unique smooth curve with that function field.
Yeah, that's true. Yeah.
Which is not true in higher dimensions.
Yeah. The curves case is very special, and especially if our curves are smooth, irreducible, then yeah, all these nice things are true.
But that curve is unique, corresponding to
Right. Yeah, there exists a unique curve with the given function field of transcendence degree 1. Yeah, that's okay. So I defined this peak 0 of X, and this is called as degree 0 divisor class group of X. So if you are familiar with line bundles, then this is also a group of degree 0 line bundles on X. Basically, on curve, divisors correspond to line bundles. I think we also saw this in Sudarshan talks. So these are also, so this peak 0x also parameterizes degree 0 line bundles on X. And then I just quickly want to discuss the push forward and pullbacks of divisors. So along some map of curves. So let's say we have a map of curves phi x to y, x and y are curves, and let's say this is a non-constant map. Then again, in this particular situation, any non-constant map is surjective and it has finite fibers. So in such case, one can define push forward phi lower star and pull back phi upper star on the divisor groups, and the definition is quite straightforward. So any such formal sum nxx is mapped to nx phi of x under a push forward map, and under pullback nyy summation nyy is mapped to summation ny, and for each y, as I said, there are only finitely many x in the fiber over y, right? So you take those x and multiply them with the corresponding ramification index of x over y. Okay, sorry. So it should be here x, not nx. Right. So this is these are the maps on divisor groups, push forward and pullback maps, and then actually they descend to the map on peak 0. So that means the degree 0 divisors map to degree 0 divisors and principal divisors map to principal divisors under this phi lower star and phi upper star. Okay. So so with this just rough brief review, let me come to a definition of elliptic curve over arbitrary field. So an elliptic curve over K, where is a curve of genus 1 together with a K rational point, which I denote by 0e. So I mean, any genus 1 curve, if it has a if the set of rational points is non-empty, then it can be given an elliptic. It can be made into an elliptic curve. And I hope, I mean, I'm just assuming that people know what is the definition of genus in the language of algebraic geometry. Here one has to use the, probably if you know Riemann-Roch theorem, then that contains the definition of genus, or otherwise you can define genus to be the dimension of the canonical bundle on your the space of Yeah. I mean, okay, so the canonical bundle, you can look at the sections of canonical bundle on X that forms a vector space and its dimension is by definition the genus. Okay, so what is special about elliptic curves or genus 1 curves together with a given rational point? The fact is that an elliptic curve over K is actually a group variety over K. Or if you're in modern language, it's a group scheme over K. So what does this mean? It has a group structure and the group multiplication and inverse. These are the maps of algebraic varieties. And in this group structure, the identity is the given K rational point. Moreover, this group structure is abelian. So let me give you one sort of proof of this on the K rational points of E. So on the K rational points of E, one can define a map from EK to degree 0 divisor class group of E, where you send any point X, K rational point, to the divisor X minus O 0 E and take its class in divisor class group. And one can prove that this is a bijection by Riemann-Roch theorem using Riemann-Roch theorem. And since this peak 0 is obviously a group, this you can transport the group structure from peak 0 E to EK under this bijection. So yeah, so one can prove that the set of K rational points on elliptic curve has a abelian group structure by Riemann-Roch, but this fact says something more, that the whole curve, not just K rational points, has a group structure. Okay. So if the characteristic of K is not equal to 2 or 3, then actually E can be given by equation, the vanishing set of y square z minus x cube minus ax z square minus bz cube inside a two-dimensional projective space over K for some A and B in small k. So Buhan actually began with this definition of elliptic curve, but one can actually deduce this, right, from the definition that I gave. Again, I am only going to say many things just as a facts because I want to arrive at the main theorem in 1 hour talk. Right. So now, once we have elliptic curves over any field K, then there is an important notion of a map between elliptic curves. So let E and E prime be two elliptic curves over K. Then an isogeny is a map alpha from E to E prime, which is non-constant, and it takes the identity of E to identity of E prime. Now, since as I said, the non-constant maps between curves are surjective and they have finite fibers, one can actually give equivalent definition of isogenes. So what are the equivalent definitions? So basically isogenes are same as non-trivial group homomorphisms of elliptic curves. And also isogenes are the same as surjective group homomorphisms with finite kernel. All these are equivalent definitions. So we are just looking at maps which are surjective group homomorphisms and they have finite. Well, I mean, once you have a surjective group homomorphism, it is automatically going to have a finite kernel because the maps between curves have finite fibers, and since this is a group homomorphism, the fiber over 0 of E prime is going to be a subgroup of E, and that's the kernel. Okay, so these are just some equivalent definition of isogenes. Next, I want to now talk about isogenes. So given an isogeny of elliptic curves, alpha, of course, we have induced map on the function fields in the other direction, right? Ke prime to Ke. And I'm denoting it by K alpha. So this is a map on the function fields. And then we define the degree of the isogeny to be the degree of the this extension. So, I mean, given any we have this map on the function fields from Ke prime to Ke, and Ke prime can be sits inside Ke via this map, and the corresponding extension of the function fields has a finite degree, and that degree is defined to be the degree of the isogeny. And similarly, we say that alpha, the isogeny is separable if the field extension, the corresponding field extension is separable. So that is Ke over the image of K alpha is separable. So clearly, if the characteristic of K is 0, then any isogeny is going to be separable because all fields of characteristic 0 are separable. So inseparable isogenies occur only in positive characteristic case. Now let's look at some examples to get some idea for those who haven't seen these things. Okay, so on elliptic curves, since these are abelian groups, abelian group varieties, you have a map multiplication by n, which is a group homomorphism, and this is called as multiplication by n map, and it's denoted by n in the square brackets. So this one can check that this has degree n square, and this is separable if and only if the characteristic of K does not divide n. And another important example I want to discuss is in the positive characteristic. So let's say the characteristic of K is positive, equal to some prime P.
In the case of isogeny, this field extension Ke,
yes,
of im K alpha, is that a cyclic extension?
If the degree is prime,
No, degree, yeah, but is that the is it? I think it's Galois. It's abelian. Everything is abelian, right? Yeah. And so, is the Galois group a cyclic group?
not always.
No.
No, not always.
No, I see. No, you're right.
And also, it's I mean, it can be inseparable, right? I mean, I said, in fact, in characteristic P, it can be it can be inseparable also. Like, so in the example 2 I'm going to discuss, it is inseparable extension, which is the P power map, Frobenius P power map. So in characteristic P, we have a map I denoted by sigma P, which is not an endomorphism of E, but it goes from E to E sigma P. So I will say what E sigma P is, but let me first describe what this map is. So it is called as Pth Frobenius map, and what it does on points. So for any K prime over K on K prime points of E, it takes any point x, y, z to its pth powers of x, y, and z. So my if my elliptic curve is defined over Fp, so that means it is the zero set of some homogeneous equation with coefficients from Fp, then this codomain is same as E. But in general, this E sigma P has equation in which you raise the powers of the coefficients of the equation of P. Okay. So if E is defined over Fp, then this sigma P is an endomorphism of E. But nevertheless, sigma P is isogeny from E to E sigma P. And this isogeny is inseparable, and it has degree P. So by this, I mean, if you look at the corresponding field extension of the function fields, then that extension is inseparable. So, I mean, it's not I mean, all these facts are not straightforward or obvious, but they are also not very hard. And the references I will give at the end, 2 and 3, they have all the detailed proofs of these things. Okay. Okay, so let's move on. Right. So now, if you recall from your algebra field theory, that any extension of fields, you can break it into 2 parts. One is purely inseparable and the other part is separable. Okay. So similarly, we can express any isogeny as a product of or the composition of a separable isogeny and some Frobenius power. Okay, so what does this fact say here next is that this Frobenius isogeny sigma p is the only sort of it's the only inseparable isogeny. So okay, so let me read this. So if the characteristic of K is positive, P greater than 0, and alpha is an isogeny from E to E prime, then alpha can always be written as the composition of a separable isogeny times composed with some power of the Frobenius, for some separable alpha safe and some positive non-negative integer n. So in positive characteristic, the Frobenius is the only inseparable isogeny. And moreover, since all isogenes have finite kernel, one can ask what is the size of the kernel, right? So the kernel of the size of alpha is the degree of the separable part of alpha. Okay, so let's go back to our examples 1 and 2. So in example 1, I had this multiplication by n isogeny. The size of the kernel of multiplication by n is the same as the n origin size of the n origin points of elliptic kernel. So this is the notation for n origin points of E. And we know that the degree of multiplication by n map has n square, as in I said that as a fact. So, and then by combining these 2 facts, we see that if the characteristic of K does not divide n, then the nth origin has size n square. Nth origin of any elliptic curve has size n square. And in example 2, the Frobenius has a trivial kernel because its separable part is just, from this fact, the separable part is just 1, or identity you can take. So it is 1. So this Frobenius is actually a bijection on where is it? This one. But still it has degree P. So in characteristic K case, the things are characteristic P case, where P is prime number, things are not intuitive sometimes. Now using these facts, I want to show something. I want to show that what happens when what happens to the multiplication by P map when characteristic of K is P. Okay. So let's say the characteristic of K is some prime P, and let's have a look at the multiplication by P map on some elliptic curve over K. Then we can write P as P safe composed with some power of the Frobenius. Now we know that this multiplication by P has degree P square. So the P square is equal to the degree of multiplication by P, which is equal to the product of degree of P safe times P power n. The degree of sigma P is P. And then what does this say? And clearly we know that this n is not 0 because multiplication by p, since the characteristic of k is p, we know that multiplication by p is not separable. So there is some power of Frobenius appearing in the multiplication by p. So this equation says that since n is strictly greater than 0, oh sorry, n is where it should be n is strictly greater than 1. I want some Frobenius. Sorry, here again. So this says that so here you have at least p, and here you have p square. So the degree of p shape must be either 1 or p, and we know that the degree of p shape, the separable part of p, is same as the p torsion of elliptic curves by this thing. The kernel of alpha is the degree of the separable part of alpha. So what does this say? In characteristic p case, the p torsion of elliptic curves is either 0 or isomorphic to z mod p z. Okay. Right. So this was some discussion about, right. Oh yeah, there is one more important definition. But so let me ask if there is any questions. I am just, I guess, writing down some definitions and facts. I haven't shown anything. But at least up to this, if it is clear everything, although it's yeah.
Just a comment.
Yeah.
I think the part that you erase 0 and write 1, I think the 0 is true as you write n greater than 0, not greater. For 1, you need greater than or equal to 1 in both lines.
Yeah, sorry, the next line is wrong. I wanted to say. Yeah. Is this correct? The next line, it should be n greater than 0. Yeah.
Thanks.
Right. Next important definition in this topic is the dual isogeny. So given an isogeny alpha, there exists a unique isogeny alpha dual from E prime to E in the opposite direction, such that alpha composed with alpha dual composed with alpha is the multiplication by degree of alpha map. And in such case, we say alpha check as the dual isogeny of alpha. So there now I want to come to main proposition of this section, and this is the only thing I am going to prove in this whole talk, as in the complete proof. All others are going to be just some ideas or sketches. So the next proposition says that in characteristic P, if you are given a degree P isogeny, then there are only two possibilities. Either that isogeny is the Frobenius or it is the dual of the Frobenius. So okay, then let me read the proposition again. So let characteristic of K is some prime P, and let alpha is a isogeny of degree P. Okay. Then either alpha is sigma P, the Frobenius, or alpha is the dual of Frobenius. And of course, if alpha is the Frobenius, then E prime here is going to be the E sigma P, which if you recall, the notation was sigma P goes from E to E upper sigma P. And if alpha is the dual of sigma P, then E prime is the E upper sigma P inverse. Okay, so let me prove this. It's actually very easy. That's why I decided to include it in the talk. And it's actually basically just putting together all the definitions and facts I mentioned. Okay. So what we want to show that if any degree P isogeny is either Frobenius or its dual. So there are two cases, right? Alpha is alpha inseparable and alpha separable. So if alpha separable, then alpha has to be sigma p. It's clear. So if alpha is inseparable, then I will show that alpha dual is the Frobenius. Then that will prove the proposition. So how do we see this? So if alpha is separable, then the kernel of alpha is the degree of the separable part of alpha. But separable part of alpha is alpha. So the degree of kernel of alpha, the size of the kernel of alpha is the degree of alpha, which is equal to p. Because alpha is a degree p isogeny. Now let's look at the dual of alpha. We know by definition that alpha dual composed with alpha is the multiplication by degree of alpha. And we know that the degree of alpha is p, the alpha dual composed with alpha is multiplication by p math. Okay, and what does this say? If you take the kernel on both sides and then take the cardinality of the size, you will get the kernel of alpha dual, size of the kernel of alpha dual times the size of kernel of alpha is the size of kernel of multiplication by p, which is the p torsion of e. And we have seen that the size of p torsion of e is either 1 or p. And we know that the kernel of alpha has size p. So this implies that the size of the kernel of alpha dual is 1. So in some sense, this part here can never be 1. It has to be p, and then this p will imply that this is 1. And then that implies that alpha dual is inseparable, and therefore alpha dual is sigma. So the upshot of this section is that in characteristic 0, all the isogenes are separable between elliptic curves. In characteristic P, there are inseparable isogenes. And
alpha dual is actually a bijection.
Alpha, sorry?
This alpha dual,
yes,
is actually a bijection of.
Yeah, it's also bijection. As in general, are you saying, or in this particular case?
I think consequence of this theorem, right?
Right. In this proposition, what we have showed is that alpha is either sigma p or its dual, and both sigma p and its dual are bijections. So alpha is bijection, but in general, it is not true.
So what is the degree of that alpha dual?
So degree of alpha dual is same as the degree of alpha, degree of sigma p. Okay, so alpha dual is sigma p. And degree of Frobenius is p.
Map as such, but just the degree of alpha dual is just a map of curves.
Alpha dual is a map of curves. Yeah.
So what is its degree?
So it is p. Because alpha dual is the Frobenius map, and I said that Frobenius has degree p. Do you? Is it something confusing here? So both sigma p and its dual, Frobenius and its dual, they both have degree p, and their composition is the multiplication by p map. Okay.
Oh, I see.
So multiplication by p map, and which has degree p square. So yeah. Okay. So the upshot was, I was saying that in characteristic P, the degree P isogenes there are only two possibilities for degree P isogeny. One is the Frobenius and the other one is its dual. This is also sometimes called as Verschiebung. It's a German word, but we will just say it's Frobenius dual.
What's the German word?
Verschiebung. So okay, I will write it.
Verschiebung.
Yeah, the meaning is shift. So okay, so now I am already over my time. So now we come to the second part of my talk. It's about Jacobians and the action of Hecke operator on J0. I have to be fast. And actually now the talks get very, the content gets very advanced and maybe hand wavy also. Right. So first I want to just say what Jacobians are. So let X be a curve over K and of genus G. Now we don't restrict to genus curves. Then there exists a smooth irreducible projective variety denoted by Jx over K and called as Jacobian of X. This has dimension G. And what is the defining property of this variety? Such that the K points of this Jx curve is the degree 0 divisor class group of X. So we saw in the case of elliptic curves that their K points are in bijection with the degree 0 line bundles or degree 0 divisors on elliptic curves. But this is true in higher dimensions also. Given any curve X of some genus G, there exists a smooth irreducible projective variety of dimension G whose K points actually parameterize degree 0 line bundles on that curve X. And that is called as Jacobian of X. And again, like elliptic curves, Jx is a group variety over K. The group structure is abelian, and such objects are called as abelian varieties. So these are the higher.
Sorry, a question.
Yeah.
What happens for genus 0? Is the Jacobian is a well-defined thing or not?
Genus 0, Jacobian is 0 or the trivial, you can say, because yeah, genus 0 means your so in complex settings, this Jacobian X can be defined as the quotient of okay, let me write it this time. So this can be defined as the quotient of the canonical bundle. Also the section, sorry, not canonical bundle, the sections of the canonical bundle on X. It's dual vector space and modulo the first homology of X. Now, now if the genus is 0, then this numerator here is 0. So I believe this Jacobian is just 0.
Oh,
Or just
thanks.
1 point. As a variety, it's just 1 point. You can say it's as a geometric object.
Yeah, thank you.
Okay, so so these abelian varieties are the higher dimension analogs of elliptic curves, and the Jacobian of any curve X is an abelian variety of the dimension equal to the genus of that curve. So yeah, so I just note that if the curve is E, then the Jacobian of the elliptic curve is actually the curve itself. There is a canonical isomorphism between the Jacobian of E and E. And similar to elliptic curves on abelian varieties, we have, since these are group varieties, we have multiplication by n map and similar notion of isogeny, dual isogeny, and so on. And if I have a non-constant map of curves, then as I explained the push forward and pullbacks on the peak 0 of X, peak 0 of the corresponding curves, involved curves, they also exist on the Jacobians, these maps, push forward and pullbacks. And these maps are then the maps of varieties. As I said, in the complex setting, when X is a curve over complex numbers, then there is a way to define Jacobian using an analytic way of defining Jacobian. The Shaunak briefly talked about this in his last talk. But for general curves, the existence of such Jacobian is not easy. It's difficult. It uses advanced algebraic geometry, and the Mumford. So the Mumford has a book called Abelian Varieties. There you can see this. But yeah, we just want to know that there exists such an object for this. Okay, now we come to our modular curves. So I have actually, let me 15 minutes and then I will have to be quick here. So let's now come back to the modular curves. We have, recall the modular curve x0n attached to the congruence subgroup gamma 0n, which is the quotient of the extended upper half plane by gamma 0n. And since this is a curve, we can talk about its Jacobian. We denote it by J0n. And then we have the action of Hecke operators on the space of weight 2 curve forms, right? We want to understand the action of these Hecke operators now on the modular curve and on its Jacobian. So for that, we reinterpret this Hecke operator as a map on the set of lattices in C. So recall that if tau is a point in the upper half plane, then let's say lambda tau is the lattice z direction z tau. Then recall that what does PP do on F in S2 gamma 0n. So PP of F, when evaluated on tau, is actually, if you see the definition from any of the previous talks, TP of F of tau is actually P times summation of F tau i's, where what are tau i's? Tau i's are those points in the upper half plane such that the corresponding lattice is a sublattice of lambda tau of index P. So what is this interpretation of TP? You can think of TP as a map of lattices which takes a lattice, let's say lambda tau, to the sum of sublattices of lambda tau of index P. This is the interpretation you understand. Now recall that lattices in C up to homotopy are same as the elliptic curves over complex numbers. The correspondence is given by lambda corresponding to C mod lambda, right? And then the sublattices of lambda will correspond to surjective maps of elliptic curves with finite kernel if the sublattice has a finite index. So basically, sublattices of finite index correspond to isogenes of the corresponding curves. And then index P sublattices will correspond to degree P isogenes of elliptic curves. Okay. So let's so what is so let me precisely define the map TP for P not dividing n on the Jacobian J0n. So recall the modular description of this modular curve x0n from Shaunak. What was the description of the x0 and P? The non-cuspidal points, that is the affine part of this modular curve, describe the pairs E comma D up to isomorphism, where E is an elliptic curve and D is the cyclic subgroup of E of order np. There, okay. So, but I can now see the D is a cyclic subgroup of order np, and p does not divide n. Then I can write D as cyclic group of order n and some cyclic group of order p. So in other words, I can write this pair E comma D as a pair of isogeny of elliptic curves and cyclic subgroup of E of order n. So yeah, so we are going to use this description of points of x0 and p. So any point is a degree p isogeny and cyclic subgroup of order n. Okay. So now with this description of x0 and p, I have two natural maps from x0 and p to x0 n. So one is pi1 and the other one is pi2. So pi1 takes E. So pi1 takes alpha comma c to E comma c. So alpha is isogeny from E to E prime. And pi2 takes this point to E prime comma alpha c. I mean, basically, so this map forgets the degree p part of the isogeny, and this map takes the quotient. So E prime is the quotient by the degree p subgroup. Okay, so we have these maps on the modular curves, and then I said that the maps give rise to push forward and pullbacks on the Jacobians. Here we have this pullback, which is from J0 into J0 NP of pullback of pi1 star, pi1, that is pi1 star. And pullback of pi2 star will be from J0 into J0 NP again. But here I take the dual of that. So then again I get a map from J0 NP to J0 N. And then the action of Hecke operator is actually the composition of these two maps. The action of Hecke operator on J0 N is actually the composition of these two maps. So okay, maybe this is a bit very fast, but on the divisors of x0n, the TP is very explicit, and let me describe that. So on divisors, on divisor class group, here I'm not taking the zero part, I'm taking the whole divisor class group. If you take the class of point E comma C, right, where E comma C is a point of x0n, so E is a elliptic curve and C is a cyclic group of order n, then TP basically takes it to the summation of classes of points E prime comma alpha C, summation over all degree P isogeny from E to E prime. So now you can maybe sort of see the similarity between this TP map and then the usual Hecke operator map. Right. So now I come back to my final section about the Eichler-Shimura section and the sketch of the Modular. Okay, so this is going to be very brief, and but let's see, and this is the most probably the technical part. So so far we did not. So far this was over. Everything was over C, but now we use the fact that the modular curve is defined over Q, and then we want to go modulo P, reduce modulo P for all primes not dividing me. So what are the main points here? We know that x0 is defined over Q, and one can show that it has a good reduction at all the primes P not dividing the level n. In fact, as a group scheme, it is defined over in Z attached with 1 over n. So this modular curve is defined over this subring of Q. So you can actually reduce modulo P for all at all primes not dividing n. And the same holds for the Jacobian of the modular curve as well. Okay, so then reducing modulo P, we have curves which are defined over Fp. So this is a curve over Fp and this is a variety over Fp of a dimension, the genus of the modular curve. And similarly, the Hecke operator action also reduces modulo P. So, and so I am denoting that this reduction also by the same letter Tp. So we have this Tp as the endomorphism of the mod P Jacobian over Fp. Now, as I said, this Jacobian is an abelian variety, and similar to elliptic curves, we have Frobenius and dual of the Frobenius on any abelian varieties, basically. In characteristic P, one has these two maps. Now, what does Eichler-Shimura relation or says that in this endomorphism ring of J0 and Fp, the Hecke operator action is actually the sum of the Frobenius and its dual. So also on J0 and Fp, the Hecke action is basically Hecke action at P is the same as you first apply Frobenius and then apply its dual and then add. So here it's for all primes not dividing any. But anyway, I mean, we always have P not dividing any. From now on. Yeah. So this is the Eichler-Shimura relation. It's and we now see how it can be used to construct Galois representations with the property that the trace of the Frobenius captures the Fourier coefficients of the modular forms. I have sort of 3 minutes left, but I will cover this part.
You can take 5 minutes more, maybe. Go ahead.
Yeah. So, okay. So, so are there any questions regarding the statement of the Eichler-Shimura relation? I guess it's very clear. I just want to give a sketch of this Eichler-Shimura relation, why it's true. So notice that this holds over Fp. So in characteristic P. So we want to look at the modular curve over Fp, and similar to x0n, this x0n Fp also has moduli description, and whose non-cuspidal points of x0 and P, the affine part y0 and P, that means is the set. Sorry. The points correspond to the pairs E and C, where now E is an elliptic curve defined over some extension of Fp, so E over Fp bar, and C is the cyclic subgroup of order N. So similar to x0, we have a description of the points of x0 and P. And now if you look at the action of Tp, yeah, on divisors of x0n, so this I denote by star, this explicit action. What does it do? The Tp takes any elliptic curves to the sum of elliptic curves. Any E comma C class to E prime comma alpha C, where alpha is the degree P isogenic from E to E prime. So so I'm going to show this relation on peak zero part of the Jacobian. So this holds on the whole Jacobian, but I will, for this sketch, I'm just going to show it on the peak zero part. But on peak zero part, this star, the explicit Hecke operator action, what does it say? And the proposition from the section 1, it says basically that is clear, right? Because from the proposition from the section 1, if you recall that in characteristic P, there are only 2 degree P isogenes, sigma P and sigma P dual. So I mean here for this for the summation is basically over only two isogenes, and that actually I mean that is the main idea here in this Eichler-Shimura relation. Okay. So is the sketch clear? And only so the main point was this proposition, which that the only degree P isogen is in characteristic P are the Frobenius and its dual. And then the explicit description of the Hecke operator. Right, now let's come back to the main theorem at the beginning. So this is right. So we have so for okay, now we introduce another prime. So for any prime L, one defines Elliptic Tate module. So what is this? So Elliptic Tate module of the Jacobian over Fp is the inverse limit of all L power torsion points of the Jacobian. So the Jacobian is a abelian variety. You can look at the L torsion points of this group. Take the inverse limit over all n. This is a free module over ZL, the Elliptic integers, and then tensor it with QL. Then you get a QL vector space, and this has a dimension 2G, where G is the genus of X0. But now it's not just QL vector space of dimension 2G, but it also has the action of the absolute Galois group of Fp, because absolute Galois group of Fp acts on all these L torsion points. And therefore it also acts on the inverse limit. And now here inside this absolute Galois group, I have Frobenius, which is the generator of this group. And the sigma p action, which is coming from the Frobenius of J0 and Fp, it coincides with the Frobenius action of this group. Okay. So so now on this Tate module, Elliptic Tate module, it's called actually the rational Tate module. I haven't written the word rational. So by the Eichler-Shimura relation on the rational Tate module, we have these two equations, that the Hecke operator is the Frobenius at Frobenius P plus Frobenius P dual, and this anyway we have, right? This comes from the fact that the Frobenius and the composition of the Frobenius with its dual is the multiplication by P. This I mentioned this for the elliptic curves case, but this is also true on abelian varieties, right? So we have these two relations, and then one can easily check that on this Elliptic Tate module, we have this relation, that the Frob P square minus TP times Frob P plus P equal to 0. Okay, so we are not quite yet there. We want to go to characteristic 0, from characteristic P to characteristic 0. Why? Because in characteristic P case, I have the action of the absolute Galois group of Fp, but I want a representation of the absolute Galois group of Q, right? So then there is this fact that if I take my prime L not dividing N and P, then the reduction mod P map on the Elliptic Tate modules is isomorphism. So here on the left hand side, now I'm considering Elliptic Tate module of the J0 and defined over Q, not Fp. And on the right hand side, it's the reduced Jacobian. But now on the left hand side, now I have the action of the Galois of the rationals. Okay. And then this isomorphism is also.
This would be quite non-trivial, right?
Yeah. I mean, all these statements are very non-trivial. I just want to give. which statement exactly you're talking about?
This reduction and its original over Q thing are both are isomorphism.
Yeah. It's well, it is non-trivial, but it's also not very hard.
Okay.
Yeah, right. Okay, now let's. Okay, so now, yeah, we want to attach a Galois representation to weight to correspond, right? Perspective eigenform. So far we have this equation, but now we want the Fourier coefficients of the modular form instead of your TP. So now we corresponding to this F, we have a ring homomorphism phi of F from the big Hecke algebra. So this is the Hecke algebra generated by all Hecke operators at P, not dividing the wavelength. And this ring homomorphism basically maps the Hecke operator TP to the Fourier coefficient at P. And now this big Hecke algebra acts on my Jacobian. So the kernel of this ring homomorphism also acts on the Jacobian. And what we do is the following: we take the quotient of the Jacobian by the action of the kernel. And now this quotient is, so recall that the original Jacobian is an abelian variety of dimension G. So we won't get two-dimensional representation, but we will get 2G dimensional representation. But now this quotient is actually an elliptic curve over Q. Okay, and then the desired Galois representation is the rational Tayloric Tate modulo of this elliptic curve AF.
Can you repeat this last point from the modular forms?
Well, I mean, so corresponding to modular form, you have this ring homomorphism which maps Hecke operators to its Fourier coefficient, and then we take the quotient of the Jacobian by the action of the kernel of this ring homomorphism on the Jacobian. So I said that the Hecke operators act on J0n. So you have the action of this Hecke algebra on J0n. So you have the action of this kernel, which is the ideal on J0n. So this makes sense. But this, I mean, what is non-trivial is that this quotient is actually an algebraic variety. So quotient of varieties need not be algebraic variety, right? So this quotient is algebraic variety, and moreover, it's an elliptic curve. So when you quotient out this 2G dimensional variety by this, you actually get a variety of dimension 1. And then you look at the Tayloric rational Tate modulo of this elliptic curve. Now this is going to be two-dimensional QL vector space equipped with the action of the absolute Galois group of Q. And then on this, now you have the same relation, but TP replaced by AP. Okay, so this is just the rough sketch. Even I don't understand all the details, but what I have understood, I can explain. And yeah, so this finishes the talk. The references I already talked about the first and the fourth reference. The second and third I used for.
Where did you use Major's theorem, and what is the Major's theorem?
Oh, Major. So no, I did not use Major's theorem, but these are the notes of the course on Major's theorem. But it also has lectures on Eichler-Shimura relation.
So which Major's theorem is notes based on?
It says what is the size of the torsion part of the elliptic.
Okay.
Elliptic curves.
Mm-hmm.
The rational points of elliptic curves defined over number fields. The torsion part, the Major has a theorem, right? The torsion is not the torsion group is like, there are only finitely many possibilities for the torsion. So that's the theorem, and the Andrew Snowden gave a course on that theorem, and They are very nice lectures. Both, so these 2 and 3 are very nicely written lecture notes, and they are available online. Actually, yeah, I mean, the first one I don't have a very good impression of this book, but anyway, it's the standard reference for modular forms. The fourth one is also very nicely written. Okay, yeah, so I finish here. So sorry for taking me.
Okay, thanks Mihir for this very nice talk. So from the audience, are there any questions, comments, something you would like to discuss?
I have a question.
Yeah.
Is the construction of AF from F? Yeah, you start with F and construct an elliptic curve AF.
Right.
Is this construction is the course of the modularity conjecture? For modularity, we start from an elliptic curve and we want to construct a modular form.
So modularity theorem conjecture states that for any elliptic curve over defined over Q, you have a surjective map from some modular curve to that elliptic curve. So here we, yeah. So I mean, in the modularity theorem, you start with some elliptic curve defined over Q, right? As far as I know.
Yeah, but in an equivalent form, the modular that for an elliptic curve over Q, there is a modular form with
yeah,
rational integer coefficients that with blah 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 for properties
right.
in
Yeah.
Galois representation part, for
yeah,
example.
so that yeah, go on.
I mean that is this construction is the converse of that, as I heard that at the first there was a converse to modularity that from a modular form people could construct elliptic curves, and the conjecture was that, okay, what about the converse? I mean, that is this that construction, that converse?
So this no, I think so modular. Okay, so modularity theorem says that every elliptic curve is modular, and by that they mean that the Tate module attached to the elliptic curve comes from the Galois representation attached to modular forms, right?
Yes, yes.
Yes. So I think this theorem will imply modularity theorem for some elliptic curves. So it's not like any converse or anything like that. So this is, yeah, I mean, you are right. This is the way of attaching Galois representation to modular forms. So so you can view this as the dimension 2 case of the Langland's philosophy, which so the Langland's philosophy says that there should be a Galois representation attached to attached to every automorphic representation. There should be a bijection between automorphic representations and Galois representation. So modular forms are GL2 automorphic forms basically. So not dimension 2, sorry, GL2 automorphic forms. So this is one way of that Langland's conjecture. That this is from automorphic side to Galois side. But the relation of this with the modularity is, I think this is used to show them in the modularity.
I mean, but what you said, I mean, maybe this this construction of Eichler-Shimura is in some sense Galois to automorphic side of Langlands, maybe. As we have, as always, we have we all have Galois representations attached to, for example, elliptic curves, and for construction of Galois representations attached to modular forms, at the end we use an elliptic curve. So in some sense, maybe it's
okay.
automorphic, going geometry to analytic part, I mean. in some sense. Okay, thank you.
Yeah, I mean, yeah, I agree with you. Yeah.
Thanks. Thank you for your nice lecture.
Mihir, so maybe I might have missed that point, but is it possible to see from the proof that why this representation rho FL is odd?
Oh,
I mean, it maps complex conjugation to the determinant of the
complex conjugation maps to -1, but yeah, I don't know. I don't see that. Maybe,
okay.
I'm sorry.
No
actually
problem.
I under the last part I understood the least, so I.
Okay, thank you.
Yeah, sorry. But it's an odd representation.
Yeah.
Which I did not write it down.
Yeah, thank you.
So are there any questions? Other questions? So, okay, I think we can thank the speaker again for his talk.
Thanks, Mihir. Thanks, Luca, for sharing this.
Yeah, my pleasure.
Maybe we stop the live stream also.
Yeah, but I'm not longer your host.
No.
Yeah, but I'm not sure I can.
I'm asking Ganesh.
So I'm sorry, I have to go immediately. So when you see
Yeah, you can leave.
Yeah. Bye.
Thanks.